class on three things, okay? Interior, exterior angles of polygons, kind of like what we did last class and the class before. You know, the sum of the interior angles, the sum of the exterior angles, the number of sides, that kind of thing. Then we also are going to have on tessellations, which polygons tessellate versus which ones don't, and finding area of regular polygons. You're going to have a short 9-problem quiz. It's not going to be very long. You won't have but more than a half an hour to take it, and that's going to be it, and we're going to keep going, okay? But you'll have that on Tuesday of next week, unless you are in the other class and you'll have it Wednesday. But let's review problem 22 as something to think about for the test. So page 632, number 22, we are looking at a hexagon. So let me draw a hexagon here. And in this problem, we are told that the apothem, not that you know what that is or even care, but this distance or this length is 8 radical 3. Okay? Notice it's not a radius. It's just a distance. It's like the height of the triangle if you were going to draw the triangle. So I'm just going to go ahead and draw all the radii in. Okay? And we are going to look at finding the area of one of the triangles. So we know as a plan, we have 6 of these congruent triangles. The formula for a triangle is 1/2 base times height. We know the height is 8 radical 3. We now need to find the base. Okay, that's the only missing piece to it. So if we draw it a little separate, and we know that we have 8 radical 3 here, how do I find the base? Tell me what I need to do. Where do I start with these? Every time I'm looking for what? The angle at the top, right? So I'm going to be looking for this angle here. How do I find that angle? 360 divided by 6, and that will give me the entire top angle. So what is that? 60, and then I'm really going to do half because I'm really worried about just this 30, 60, 90 triangle right now. So I know that this angle is 60. This angle is 30. I'm given the short side, aren't I, in this problem? Is that right? Or did I do it wrong? I did it wrong. Where did I place the 60? Right, and it's really half of that, isn't it? Because the entire thing, this entire angle is 60. This entire angle is 60, which means this little piece right here is really 30. Would you agree with that part? Okay. Just making sure you're following along. So I'm not given the short side. What am I given? The longest leg. So I know that's 8 radical 3, which means the short side is going to be just simply what? 8. Good. Which means the entire base is good. So I know that the base is going to be 16. And it's a matter of just simply multiplying at this point. Half of 6 is 3. We'll just multiply them on the calculator. It's fine. So we have 3 times 16. Oops. 3 times 16 times 8. So I had 384 radical 3. And that would be the exact answer, okay? Hopefully that's what the book got. It is, so we're good. I guess the units were inches squared, so. Okay? How are we feeling? Okay? Got a question, Marvin?
Yeah, I want to look at the apothecary formula more easier.
It's an extra formula you would have to memorize, but I'm not going to make you memorize it. If you want to do it that way, it would not be wrong. But I'm not going to teach it to you. Okay. All right. We good? Any questions on what is going to be on the the quiz next class? No, you just wouldn't be exact. So if I did 384 radical 3, 384 square roots, 384 square roots of 3. I can't type in today. Square roots of 3. 665.1 is a rounded answer. Right, but the book said to give the answer in simplest radical form. That's just the directions was the only difference there. Okay? Any other questions, Sela? Yeah, some people didn't put it in radical form, and I didn't specify, so I don't know what 108 radical 3 is, but I'll have to figure that out, and that would be the decimal approximation. And I'll give that to you if it's correct. Maybe if you gave it to me in radical form, I'll even give you 2 points extra credit, and if you gave me the rounded, I'll give you 1 or something like that. We'll figure it out. Anything else? Okay then, go ahead and take out that sheet that you guys had for me, and I'd like some volunteers to draw the pictures of a square, rectangle, rhombus, parallelogram, trapezoid, and kite. And we really actually need to specifically talk about a trapezoid. So I'm going to put a kind of a star here. Maybe we'll call it 5B, okay? And we're going to add isosceles trapezoid, because that's a specific kind of trapezoid. So we have a regular trapezoid, and then we're going to have an isosceles trapezoid. So if you could kind of add that one as an extra, maybe I'll try to give myself some room here and add it. Oh, maybe not. Well, we'll try. Okay? So add that isosceles trapezoid as the extra. So can you maybe divide your picture here, so you have one trapezoid and an isosceles trapezoid, so you can draw both, because there is a difference between the two. Okay? Most of you probably drew an isosceles trapezoid anyway, if I had to guess, but we'll see. All right, so anyone want to volunteer? Let's come up and draw some of these things. Let's go. Anybody? Go ahead. Come on, draw. I'll pause the recording. So square, I love that you drew the congruent marks, but that's not enough. What else do I need to add to the picture for a square? The 90-degree angle. So please make sure that you are also drawing 90-degree angles on the picture. So yes, all the sides are congruent, but all the angles are also congruent, and they're 90 degrees. Some defining characteristics. We're going to talk about what those are in a couple of minutes. Well, I'll just do it now. I'm going to put on all of these three the same one. They have the same characteristics or the same properties as a parallelogram. So we're going to say that it's a parallelogram. So anything that we list underneath parallelogram will also apply to a square, and it will also apply to a rectangle. It will also apply to a rhombus. Okay? Let's say that one more time. Anything that we list under parallelogram is also true for those three. And guess what? For a square, it's also a rectangle, and it's also a rhombus. So a square has all the properties of 1, 2, 3, and 4 together. Okay? So anything that's true about a rectangle will also be true about a square. Anything that's true about a rhombus will also be true about a square. Anything that's true about a parallelogram will be true for any of those. Okay? All right. So let's go ahead and list what the properties for rectangle and rhombus and parallelogram are. So let's start with the rectangle. Give me something that's true about a rectangle. That's not necessarily true about anything else. Like anything it's not always true about a rhombus or always true about a parallelogram. Give me something that's specific to a rectangle. There's two. Specific to a rectangle only. Rectangle or square. You guys, we drew it on the picture. What was it? What did we add to our picture? So they're 90-degree angles. That's specific to a rectangle and a square. We have 90-degree angles. Right angles is okay to say. Okay. We could also say the sides are perpendicular. The adjacent sides are perpendicular. That's another way to say that same thing. There's one more thing. It has to do with the diagonals. What's true about the length of the diagonals in a rectangle? Think about, you know what a diagonal is? If I drew it in, I'm just going to draw it in real quick. If I drew this diagonal in, and I drew the other one in, well, I'm drawing things all over the place. Drew the other one in, what would be the true about their lengths? They're the same. Okay? And that's only true for a rectangle. Okay? So in a rectangle, the diagonals are congruent. Matter of fact, I'm going to highlight that one because that's one way we can prove something is a rectangle. If you are ever asked to show something is a rectangle, you can just show the diagonals are congruent and that's enough. So if you have a highlighter, that is something I would suggest you highlight. Okay, I got some here. If you would like to borrow, feel free. Okay, but that's enough to prove that it's a rectangle. Now, we're going to deal with this whole what properties does a parallelogram have, and we'll deal with that in a minute. But anything in addition to what out of the norm would a rhombus specifically have? I can think of two. A rhombus has all the sides. What? What's true about all the sides in a rhombus? They're the same length. They're congruent. So we know that to be true. The sides are congruent. So we'll say all sides are congruent. We know that's true. All the sides are the same length. Not the angles though, right? If the angles were congruent, it would be a square. But for any rhombus, the sides are congruent. There's one more. Has to do with the diagonals. Anybody know? They're not the same. No. Think about it. It's slanted, so one of the diagonals is longer than the other. I'll draw it for you. So if I'm going to draw a rhombus, hang on, it's here somewhere. There. I'm going to draw a rhombus. Pretend like all those are the same length. Isn't this length longer than the other one because it's slanted? So this one is shorter. The green one is shorter than the red one, right? And if I kind of uprighted it, wouldn't it be the same? Then it's no longer, it's a rectangle at that point, isn't it? Then they're the same. Okay. So they're not the same length. But what's true about the diagonals? Look at the angles that are formed. Look at the picture first before you answer. Anybody know? The angles that are formed by the diagonals, what's true? They're 90 degrees. Boom, boom. The diagonals are perpendicular in a rhombus. Okay, so we're going to write that. The diagonals are perpendicular. Diagonals are perpendicular. That happens in another one of these things as well. Okay? There are a couple of things that have perpendicular diagonals. A couple of them. Okay. All right, parallelogram has quite a few properties, so I hope we have enough room. How many blanks do y'all have? Just 3? 4? Okay. Hopefully, I think there's 5, but we'll see. All right, so in a parallelogram, the first one is that opposite sides are congruent. True? Okay, so both pairs of opposite sides are congruent. What else do you notice? Not only are they congruent, but what else is true? Both pairs of opposite sides are parallel too, right? Okay. It's called a parallelogram for a reason. So both pairs of opposite sides are parallel as well. Okay, I think we have enough room for a couple more. The diagonals do 2 things. They're not perpendicular unless it's a rhombus or a square, because a square is a rhombus too, right? So they're not always perpendicular, but they do something. So maybe I should draw an example. Okay, so let's go back to this guy. Let me just draw a different one. Let's make it truly not a rhombus. Definitely not a rhombus, right? Parallelogram. All right, so let me draw in the diagonals for a minute. We definitely know that's the short diagonal. This would be the long diagonal. Pretend like it goes to the corner like it's supposed to. There we go. if this side was, or this diagonal was a 4, what would be true about the other side? It would also be 4. Okay? If this side was an 8, what would the other side be? An 8. So how do we say that? What do the diagonals do to each other? They bisect each other. That's what we're going to say. Okay? The diagonals bisect each other. They cut each other in half. And there should be one more. Okay. The diagonals also do something else. Not only do they cut each other in half, which we can erase because we know now, they do something to the angles, the corner angles. Any ideas? They cut them in half too, yeah. So like, in other words, this angle and this angle are congruent. This angle and this angle are congruent. Okay, they bisect the angles. So the diagonals do that as well. Okay, so I'll write it in a different color so it stands out. So the diagonals bisect the angles. And those are really the properties. I think that's all of them. Properties of a parallelogram. Just double checking on our list here. Okay, that looks good. All right, so we have a picture of the isosceles trapezoid, and I love that the isosceles trapezoid has one pair of parallel lines, so that's going to be one of the properties. Exactly one pair of parallel lines. And that's really the definition of a trapezoid, okay? And another picture could be drawn like this. That's also a trapezoid, where I have parallel and parallel, okay? But it's not isosceles. So an example of an isosceles trapezoid is the one that's drawn in red, and any old plain old trapezoid would be drawn in green. So as long as they have exactly one pair of parallel sides, we're considering it a trapezoid, okay? But in order for it to be an isosceles trapezoid, we have to have the non-parallel sides be congruent, meaning this side is congruent to this side. That we call those the legs, just like we would in an isosceles triangle. The legs are congruent, okay? We know this. There's some true things about an isosceles trapezoid. So maybe we should be specific about properties in an isosceles trapezoid. So only for isosceles only, there are some specific properties. There's two that I can think of. So if you just want to kind of draw a little bracket for isosceles only, all trapezoids have exactly one pair of parallel sides. But for isosceles only, there are a couple of things. We obviously have congruent legs. We also have congruent base angles. So we have congruent legs and base angles. Because isn't the angle across from a congruent side also congruent? So isn't this angle congruent to this angle down here? Maybe if I highlighted it would be better. Isn't that angle and that angle congruent? Those are the base angles, okay? There's one more thing that's true. It has to do with the diagonals in an isosceles trapezoid. What do you think is true there? Somebody besides Marvin. He's answered a lot of questions today. What's true about the diagonals in an isosceles trapezoid? Are they perpendicular? Are they the same length? Do they bisect angles? What do they do? They are the same length. Okay? So in an isosceles, only in an isosceles trapezoid, the diagonals are congruent. Okay? So these are all shapes you have dealt with before in middle school. Okay? All of them. I don't know if you did kites, though. Is kite new? No? You know what a kite is? Okay. They used to call it a diamond. Okay, it's not a diamond. Okay, diamond's what you wear on your finger. Okay, not a shape. I'll draw one for you here. What is a kite? So a kite has two pairs of congruent sides, but they're adjacent to each other. So this would be congruent to this, and this would be congruent to that. That's a kite. So it's just like a parallelogram. We have two pairs of congruent sides, but in the parallelogram, weren't they the opposite ones that were congruent? This one, they're the adjacent ones. Okay? So two pair of adjacent congruent sides would be one of the properties. There are some other things that are true, two more specifically. Has to do with the diagonals. They're definitely not the same length. One will be longer than the other. We call them the major and the minor. So we're going to have a minor diagonal and a major one. Well, let me draw it exactly here. There we go. What's true about them, though? 90-degree angles. The diagonals are perpendicular, I agree. And then something else is true. Something about the smaller diagonal, the minor one. What do you think is true about that one? Not the major one, but the minor one. Smaller of the two diagonals. What does it look like happens to it? Does it look like anything? It looks like it's cut in half, and it actually is. Okay? So for example, if I knew this to be a 3, this length here, the other side would also be a 3. Okay? That minor one is cut in half. Not the long one, not the major one, but the minor diagonal is cut in half. And it's bisected by the major one. Okay, it's cut in half by the other diagonal. Okay. So, a lot of properties to kind of remember here. But the good news is that it kind of looks like these things would happen anyway if you drew the picture. So what it appears to happen actually does. Go ahead and look at the second sheet I asked you guys to pick up. And it looks like this. Use a pencil, because there might be some mistakes. And I want you to look at these different quadrilaterals. And I want you to put check marks in the boxes if it's true about that diagonal. Now, we'll come back to the idea of what a D is. The D is the definition, and we'll deal with that in a couple of minutes. But put a check mark. I'll give you some minutes to work. Use the properties that we just went over. Use the notes that we just took, and kind of assimilate that information. Let's see what happens. After walking around and looking, it looks like we've kind of at least got the bottom row done. We know that in a kite, that's kind of actually, it's the definition of kite, isn't it? We should put a D there. The definition of kite is two adjacent congruent sides, right? That's the definition. So, but there are two other things that also have that property. And Jason, what was it? Rhombus and square. So it's not their definition, but it's a characteristic that they both hold. What other definitions do you see on the left? How about the second one? The second characteristic, the second is a definition of one of those. It says both pairs of opposite sides must be parallel. Both pairs. That is the definition of a parallelogram. So why don't we put a D in that column? Okay, it's the definition of it. But there are also lots of other quadrilaterals that have those properties. Rectangle, rhombus, square also have those properties. I think that's it. Is that what you guys got? Okay, good. All angles must be right angles. That's actually a definition, or part of the definition of a rectangle. Okay? But it's true for a rhombus and a square. Would you agree with that? not a rhombus. I'm sorry, just a square. I apologize. Thank you very much. It's Friday. I blame the earth. Haven't talked to you about that yet? The earth. We can blame the earth a lot for this week. You know why? I should probably stop recording, but there's a geomagnetic storm going on. Have you heard about this? Y'all got to get up with your science. Really? Okay, so we've now decided to blame the sun. Fine. All right, so let's keep going. All sides must be congruent. That's a definition of what? Not a square. It's a definition of a rhombus. That's the definition of rhombus, but it is true for a square. I agree. What is the definition of a square? Well, it's both a rhombus and a rectangle, right? So that's how you would prove something is a square, is proving both that all their right angles and their congruent sides. Does that make sense? So maybe in a different color or something you can write that both of these would have to be true to be the definition of a square, right? Okay. Exactly one pair of opposite sides is parallel. That's the definition of a trapezoid. Good. Yep. So it's a definition of a trapezoid. Are you guys noticing a little pattern here? Right? Okay. It's also true for an isosceles trapezoid. Exactly one pair of opposite sides is going to be, it's the definition of an isosceles trapezoid. Huh? You sure?
Yeah, because there's only one pair of opposite sides.
Well, let's do this if this makes you happier, which I agree with. Together, these both would have to be true to be an isosceles trapezoid. Would you agree with that? That would be the definition of an isosceles trapezoid. Both one pair of opposite sides is parallel and congruent. But they can't be the same pair. Let me give you an example. If I take the same pair of opposite sides and they were both parallel and congruent, is that a trapezoid? Because we said here in an isosceles trapezoid that exactly one pair is parallel. So we have parallel. And then the opposite sides are congruent. Can it be the same pair? Isn't this obviously shorter than the longer one? Wouldn't you agree? So doesn't it have to be a different pair? Right? So that's an isosceles trapezoid. What if you did have one pair of opposite sides were parallel? So let's just draw them. And they were also the same length. I wanted to make it a quadrilateral. All right, so there's one example. So same length and parallel made it a quadrilateral. What kind of a figure is that always? No matter what, if I always drew one pair of sides parallel and congruent, what would it be? It'd be a parallelogram. It could be a rectangle, but it has to be a parallelogram, right? Good. But if they're different sides, parallel, congruent, that would be a trapezoid. Okay, good. So you guys, if you look at the bottom, the next thing, we have this Venn diagram. Okay? I think I gave you a word bank at the top. Okay? Square, kite, trapezoid, parallelogram, isosceles trapezoid. I want you to fill in the Venn diagram using the words. And I think I'm missing a couple, so let me fill them in. I have one here, and one here, and here. Is that right? Okay, so go ahead and fill in your words, because how do they relate to one another? How can they fit? Tell me what they would do. So they're using your properties. What properties do they share? How are they different? Fill in the words. Need to. What one quadrilateral is kind of off on its own little thing? It would be this circle in the top left. It's really not anything else but its own self. What would that be? A kite, okay? I even had you add it at the bottom, didn't I? Because it's not something that was even originally part of it. And believe it or not, it's really only a quadrilateral that us NYP people deal with, okay? So there we go. Although I do believe that it is part of the 8th grade curriculum, so you should have learned about kites back in 8th grade. But if you didn't, now you know what they are. All right, so how about the other blue circle I have on the top right? One is always something else. What would that be? Trapezoid and which one goes in the smaller circle? right? Because an isosceles trapezoid is always a regular trapezoid, right? So we'll say that that's the case. So isosceles trapezoid goes here, and trapezoid goes out here. Totally agree with you. Okay. So now we're kind of working on the bigger picture. Deshay, what's the bigger quadrilateral that's left, the more encompassing one? Parallelogram. So we know that we have a big case of quadrilaterals called parallelograms. And actually next week we're going to learn how to prove that something's a parallelogram and look at parallelograms on a coordinate plane and be more specific about them. But for now, we know that what they are and their properties. And then we have three things left. We have squares, rhombuses, and rectangles. Out of those three, where do they go here? Why is that true? And you're right. Square goes in the middle. Why, Gabriel? In a Venn diagram, if it goes in the middle, what does that mean? It's part of both, right? It's part of both. So a square is both a rectangle and a rhombus. And I don't care if you put them in either, if you put rhombus on the left and rectangle on the right, it doesn't matter. But that would be the correct Venn diagram of how these things relate. On a computer, on a SOL, what if this was one of those drag and drop things? Could you drag the quadrilateral in the correct section of the Venn diagram? Could you do that here? Maybe that'll show up. You never know. Okay? Maybe not. That's something good to look at. All right, so you guys have a couple more minutes. Actually, you know what? I need to do the area problem. So part of your homework is going to be to do 7 through 13. Okay, do you see that there? So at the bottom, there's the sometimes, always, never questions. These questions here, the ones on the back as well, and then these as well. Decide what kind of quadrilateral they all are based on their properties. Okay? So this is going to be part of your homework. So just list it right there, part of your homework, and then we'll go from there. Okay? So part of your homework. All right, question. Yeah, I want you to do 1 through 7. What did I say? 1 through 13. Sorry. Yes, do them all. Yes, 1 through 13. Do all the sometimes, always, never stuff, and those, tell me what kind of quadrilateral it is. That should probably take you about 5 minutes, right? It's not going to take you that long. And we'll go over it next class. I am going to have you go ahead and take your notes out for me, okay? And we're going to add a couple of examples to find the area of quadrilaterals, okay? So title this area of quadrilaterals in your notes. Sorry today is so note intensive. I know we got to play with toys last class, but some days are more note intensive than the other. This happens to be one of those days. Sorry. Areas of quadrilaterals. Oh, today is the 20th. Okay. Huh? Today is, I thought today was. Is tomorrow? Yeah, today's the 20th. All right. So we're going to be asking, let's see how many we're going to do. So we're going to find areas of these, and I don't know time-wise whether we'll be able to solve them all the way, but at least we can get started, okay? So we're going to find the area of a parallelogram, the area of a trapezoid, the area of a rhombus, the area of a kite. So 4 things. Four, right? Things we're going to look at. The only one that has a formula, well, I guess they all have formulas. We'll write them down. And I'm going to give you an SOL formula sheet next class. I don't think I have enough copied right now. But on the SOL formula sheet, there are some of these formulas written down, okay? Some of them are there and some of them aren't. But parallelogram is, and I'll just tell you what it is, okay? So I'll give you the formula. I'm not going to ask you to memorize it because it'll be on the formula sheet. Fair enough? No need to memorize the formula if it's there. I'm not a big memorization. You already have to memorize the distance formula and the slope formula and the, what else? Midpoint formula. You got to memorize enough. Here we go. We should know this, though. How do I find the area of that parallelogram? What do you think? How do I find the length of the base? What is the base? How'd you get that, Emily? You're right. Yeah, can't I, if it's horizontal, can't I just count? I mean, if you want to do the distance formula, go for it. But it's not necessary. So I agree. She just counted. So we have 1, 2, 3, 4, 5. I didn't get, hang on. Did you get 7? I got 6. 1, 2, 3, 4, 5, 6. So 6, right? Okay. So we're going to have 6 as the length of our base. So this guy is 6. I agree. What's the height of this? How'd you get 2? Go ahead, Julian. From what to what? From the base to the... So between the top and the bottom, I mean, you could kind of draw it anywhere. I'll just draw in a couple of them. That's a height, that's a height, that's a height. They're all the same, wouldn't you say? Most often, you'll see it kind of drawn in the corner down here, like this, from one of the vertices to the base, okay? And so we can count that because it's a vertical line, and what do we get? 2. So what's the area of this guy? Okay, so it's just like, and we'll just call it units because we don't know what they are, units squared. Basic, right? We can do that. This is so 5th grade. Got it. Let's try another one. Ready? Trapezoid. This one also has a formula on the formula sheet that I will give you. And this is it.
Is the 1/2 base 1 plus base 2 is kind of like the average, I think?
It is. It's the average of the bases times the height. So it's kind of like the parallelogram formula, base times height. But the 1/2 B1 plus B2 is like the average length of the bases. Perfect way to think about it. I'm missing some information here, though. What information do I have in the picture and in the formula? I have the height. Good. So let's plug it in. I have the height is 4. Perfect. So I have 1/2 times 4. What else do I have? One of the bases, and when that is going to be 6. Why is the 5 there? Do I need it? Is it extra? Sometimes they give me extra stuff. Is it needed? Is that the other base? Okay. But I have to use it to find it. Why? I'm going to probably use the Pythagorean theorem, and that will help me get the other base. Let me show you something. I have to be told this, and I'm not actually. I probably need to tell you that it's an isosceles trapezoid. Okay, because without that information, we really wouldn't be able to solve this problem. And if I drew in the other height, these two pieces to the bottom base are the same because of the symmetry of an isosceles trapezoid. What do I know the middle portion has to be? Okay, so I already know that middle portion is 6. Good. How do I find either of the highlighted pieces? Emily said it. Pythagorean theorem. I have a right triangle down here. If I call this x, x squared plus 4 squared equals 5 squared. Right? Some of us already know what the answer is because you know the Pythagorean triple. That's okay. We'll call this x for now. X squared plus 4 squared is equal to 5 squared. X squared plus 16 is equal to 25. Subtract 16. X squared is equal to 9. X is 3. People might have known 3, 4, 5. Common Pythagorean triple. So if this is 3, what does the other yellow piece have to be? 3, which means the whole bottom base is 12. Could you figure out the area now? Good. What is it? 36. And again, we probably should write units squared here because we are talking about area. Okay, good. How are we doing so far, Daniela? It's a lot of information at once, isn't it? Head hurts. It's Friday. I get it. I think we only have 2 more, though. Okay? And the last 2 are, of course, the hardest ones. Of course. Do I have enough information to find the area of the rhombus? I do. Is there a formula for the area of a rhombus? Not that I know of, unless you use base times height because that's a parallelogram, but I don't have a height even mentioned here, so that's harder. So I probably won't use the base times height formula, okay? I'm going to use something else. Idea? The what? No. I don't have a right triangle. But I could if I did what? Thank you. If I drew in my second diagonal, I can do a couple of things. Aren't the diagonals perpendicular in a rhombus? Wasn't that one of the properties we figured out? So guess what? I do have a bunch of right triangles. What's true about all those right triangles? Are they the same? Are they congruent? It's a rhombus, so they are. So if I find the area of one of them, couldn't I just multiply it by 4? Awesome. Okay, so let's just draw one of them off to the side. And we had the hypotenuse is 10. Oh, do I have any other side measures? Which one do I have? Okay. The diagonals bisect each other, don't they, in a rhombus? All parallelograms. So isn't this 8? So all I have to do is find the other guy, don't I? Because isn't this going to be 4 of these, 1/2 base times whatever the height is? And that will be the area of my rhombus. So if you're trying to find the area of a rhombus, it's kind of a cool idea to divide it up into 4 triangles. Jeez, didn't we do that with polygons too? Triangles are everywhere, man. Okay? They're going to be in circles too. We're going to do circles in our next unit. We're going to find triangles there again. Following us around, Sela. I don't know what to tell you. Yeah. The what? 3D figure? Yes, they are. Yep, right triangles even. But you can bring in, you drop down, yes, I'll show you. They will happen. What is the missing side? What's the height? It's 6. So that would give you, — 96? 2 times 48, right? All right, and again, unit squared. Good. All right, last one. We can do it. Home stretch. We got this. Can you imagine if you were one of the 4 people with choral assessments today? Poor guys, right? They'll be okay. They have the weekend. Can I do the same thing with the kites that I did with the rhombuses? Are there 4 congruent triangles here? Not 4. I have 2 pairs of congruent triangles, though, don't I? Or could I just do this? Could I just find the area of that triangle and the area of that triangle and add it together? Wouldn't that work too? Divide it up into 2 triangles that I can find the area of. Do I have the information needed to do that? So how about the yellow one? The area of that is 1/2 base times height. What's the height? What's the base? Huh? Ooh, because you know 3, 4, 5 is a common Pythagorean triple. By the way, the diagonals are perpendicular, a reason we can do that. So we have height, and what about the base? Good, because this is 4. The entire base would be 8. Good. We're going to add to that the blue one. How'd I get what? 3? Because it'd be, well, 3, 4, 5 is a Pythagorean triple, but if you do the Pythagorean theorem, you could find it too. How about the blue triangle? 1/2 base times height. What's the base in that one? Same. Is that no, same isn't something I'm supposed to say. Okay, sorry. 8 is the base, and then the height would be 10. So we're actually given that information. Okay, and then you would just add those together. And that's it. That's not bad, right? Not too bad. All right, so you guys have 2 things for homework. Part of it is the quadrilateral. I guess you have 3 things, really. You have a quiz next class. All right, so you have a quiz next class on what? What's your quiz on? What's your quiz on? Polygons, right? Do they tessellate? What is the sum of the interior and exterior angles? That kind of thing. So you have a quiz you need to study for. In addition to your quiz, you have part of that other sheet where you had to do the sometimes, always, never stuff. So you have a polygon quiz. You have to do 1 through 13 on the handout that we did. I'll say the sometimes, always, never stuff. Helps if I can spell that. And what I just gave you on area of polygons, or area of quads, I guess specifically. But if you look at that area of quad sheet, the last 3 problems are not quads, are they? The last 3 problems are polygons. So it's a good review for you for your quiz. Fair enough? Okay, so that's your homework for tonight. If you were at oral assessments, sorry, good luck.